Hi, my name is Samir. Together with Eleftheria and virtual Dragos, we'll be presenting our work called Rabbit on efficient comparison protocols in the field of multiparty computation. So multiparty computation classically deals with the following problem: that we have a number of parties who jointly want to compute a function of these inputs, and instead of giving all these values or all this data to one single party, in which case they don't have any privacy of their inputs, they prefer doing it amongst themselves in a distributed manner. So effectively, multi-party computation is sort of this distributed computation problem where we really want to hide the inputs of these computation. Multi-party computation has a ton of applications, such as secure auctions, where we would really want to do an auction but without really revealing the bids. Private machine learning, where we potentially want to train or do inference on machine learning models without revealing the data. Genomic computations is another domain where the data is really sensitive and we would like to have privacy of that data. And then other applications include set intersection, encrypted email, and so on. So when we look at all these applications from a multi-party computation point of view, we usually distill out the mathematical functionalities needed to enable such applications, and then design multi-party computation protocols for those. So one common or one strong commonality between all these applications is a protocol for secure comparison. And in literature, it's also known as the millionaire's problem, where we would really like to take a number of private inputs, but compare them, like find what is the maximum, find which one is the minimum, and so on. So while there is a variety of flavors, sometimes they might be equivalent, sometimes they might not. In this work, we are going to focus on the following setup. We have arithmetic secret sharing of a secret x, which is in this ring, 0 to m-1. And what we would like to compute is whether this x, like the underlying secret, is less than a public value r. And so r in our case is going to be public. Eleftheria would mention the suite of protocols we are going to do in this work, and she'll also talk about how do we compare to secret integers and the protocols for that. But this is going to be the most important building block. So we compare a secret integer with a public value given by r. Even this restricted or this simple comparison protocol has a number of applications. So for instance, the moment when we want to do thresholding, where we want to figure out if a counter has exceeded a certain value which is publicly known, the corresponding multi-party computation protocol would be a secure comparison. Or if you want to find the maximum of a number of integers, and a very specific case of this is this function called ReLU, which is a very popular function in machine learning, where we would like to find the maximum of x and 0. So if x is negative, we just want to output 0, but if x is positive, we output x. So this is yet another example where the secure comparison protocol, or for instance equality, can also be built using secure comparison protocols. So that's really going to be the central part of this work. And next I'm going to briefly mention the core contributions of this work in one slide. So our first contribution is we propose a new suite of comparison protocols which exploit the commutativity of addition. These are general n-party protocols, so can be used in a 2-party, 3-party, n-party setting. And they are also secure in this arithmetic black box model. And so we can actually enable these protocols in semi-honest, honest majority, passive corruptions, malicious corruptions, all kinds of corruption models. Eleftheria will talk a bit more about these in the next part of this talk. The second contribution is the elimination of slack. And here by slack, we mean a gap or a separation between the bit length of the input and the MPC representation. In other words, if we want to compute over 80 bits of input, we frequently need to store the MPC secrets or the shares in a larger field, about 128-bit secret values. And this, as a consequence of this elimination of slack, we can enable computation over smaller data types. And Dragos is going to talk a bit more about this part of the work. And finally, our protocols are extremely simple to implement, and they are probably a handful of lines in MP speeds, and that's something that Eleftheria will again bring up in her part of the talk. Finally, I would like to introduce the relevant prior work on which we build. That's EDABITS from Crypto 2020. EDABIT stands for Extended Doubly Authenticated Bits, which is effectively a way of a very efficient way of generating arithmetic secret sharing of a secret X, as well as a bit decomposition as sharing in a Boolean field. So X is related to these Xi's by this, and then we can efficiently generate the sharing. EDABITS improves upon a prior work called DABIT, where you can generate a single bit in both the arithmetic as well as the Boolean sharing form. And it's improving that, instead of using MDABITs, you can do it much more efficiently. So that's the core contribution, using techniques such as cut and choose. And both these primitives are extremely crucial for primitives such as share conversion, which are quite useful in designing efficient protocols for comparison. With that, I'm going to pass the rabbit to Eleftheria.
Thank you, Samir. And now that the rabbit is here, let's take a closer look at it. Let me introduce you to the rabbit collection. In our work, we propose 4 different comparison protocols that take different kind of inputs each. And on the slide, you see the dependency graph between them. So at the top, we have protocol LT-bits, which implements the less than function between a public constant and a bit decomposed secret. The less than function is based on prior work, but it is essentially a generalization thereof. There are 2 differences between our LT-bits protocol and what has been already proposed in the literature. The first one is that our comparison takes place between a public constant and a bit decomposed secret, while prior work looked at a more general problem of comparing 2 bit decomposed secrets. In practice, this means that our protocol is simpler and therefore also faster. The second difference is that our bit decomposed secret each component of it lives natively in F2, while prior work depended on a bit decomposed secret where each of the bit sharings was living in FP. That's in a lot larger space, and that's again a win for us in terms of efficiency. LT-bits is invoked by all other 3 protocols that we propose. And the protocol that I would like to focus on today is the LTC Protocol. This is a protocol that implements the less than function between an arithmetic sharing and a public constant. Now let me get you through the intuition behind it. Our first observation is that we can actually compute modular sums by performing computations over the integers. How can we do that? We need to detect when a sum over a particular modulus wraps around, and when that happens, we should correct for it. To do that, we need to have a less than function that takes 2 arithmetic inputs, x and y, and returns 1 if x is less than y, and returns 0 otherwise. Now, by using this function, as I explained, we can compute a modular sum only by performing operations over the integers. So if I want to compute x plus y mod m, there are 2 different ways I can do that by using this less than function. So I will invoke this less than function if I can compute x plus y mod m, let's say somehow in a secret manner, and I will invoke the less than function between this modular sum and either of the 2 sums, x or y. Now observe that the less than function between x plus y mod m and either of the 2 summands returns 1 only if we had a wraparound. So x plus y mod m can be smaller than either of the 2 summands only if we had a wraparound. And that's exactly our wraparound detection. Now, by using this flag and multiplying this with a modulus quantity capital M, we can correct for the wraparound, as you see on the formula on the slide, by subtracting this quantity when the wraparound happens. Our second observation is that we can exploit the commutativity of addition. So first, I'd like to draw your attention at the callout at the top right of my slide. So remember, what we need to compute is a Boolean value whether x is less than capital R. And for ease of presentation, we are using a capital B variable in our diagram. Remember that capital R equals m minus that constant capital B. M is our modulus quantity. So I assume I have a secret value x in the space capital M. That's a secret. And I want to be able to somehow open a value related to this x. So what we generally do in MPC is masking this value with a uniformly random value. We call it R in our case. And then we are allowed to open this result later on without revealing any information about the secret x. So I add a uniformly random value R and I end up with the value A. Now to this value A, I would like to add the quantity capital B I talked about before. That's related to the second term in my comparison protocol. And this leads to a value small b that can also be opened as, well, it is comprised by A, which can be revealed, and a public value capital B. So here I haven't exploited the commutativity of addition, but this is a series of sums which I can perform in a different order. So I could also first compute the value C by adding capital B to my secret x. That would result in a secret value C. And then I can add the randomness to end up to the same value B. Now by combining this commutativity property, the two different ways I can compute small b, together with observation 1, how can I write modular sums over the integers, and following the red path, I can compute the quantity that just appeared on the slide. So I can compute b by computing x plus r and removing the quantity m if there was a wraparound. And then on this quantity I add capital B and I subtract my modulus quantity again if there was a wraparound in this sum. Likewise, I can do the same for the green path. Now by equating the two right-hand sides of these two equations, I end up with the following expression. This expression only contains invocations of this less than function we talked about before. And what we're actually interested in is the result less than between C and capital B. Now, from the commutativity graph, recall that C equals x plus b, and that is less than capital B if and only if x is less than capital R. If you take a closer look at the callout at the top of my slide, you will confirm this observation. So this is exactly the expression I showed you in the previous slide. I remind you, we are interested in the less than function between C and capital B, so that would be our x less than R question. And then if we rearrange the terms, this is exactly what we need to compute. 3 invocations of the less than function. Now let's see how the LTC protocol performs these operations. As Samir promised you, it's a protocol very easy to implement, and you can see on the slide is just a couple of lines of pseudocode. So first we initialize the bit length of our program, and then we continue by generating an edabit R. As Samir explained before, an edabit is a random value that lives in 2 different spaces at the same time, we have the arithmetic sharing of the value r, and we also have the sharings of the bit decomposed version of the r shared amongst our protocol participants. So first we use the arithmetic version of our EDA bit to mask our secret x, and since now x is one time padded, we can reveal this value. Now by adding the quantity capital B, which is m minus r, to the open value a, we get to compute the value small b that I showed you before in the commutativity graph. Now we are ready to compute the three less than functions that gives us their desired result. First, we invoke the LTBits function between the public value now a and the bit decomposed version of our EDA bit. Then we invoke the LTBits function on the public value b and the bit decomposed version of our EDA bit. That's the second term we saw in the equation above the pseudocode. And the last thing we need to do is to perform a public comparison. So we don't need to invoke the LTBits here because all values b small and b capital are known to all parties, so they can compute the result in the clear. So last step, just bring all these three terms together and you've got the final result, the flag that indicates whether x is less than capital R. So I've given you the intuition behind the less than a constant protocol, and this, by following the same observations, generalized to a protocol that performs the less than operation between two different arithmetic sharings, x and y. So again, we use the commutativity of addition and the way we can write out modular sums over the integers, and we get to a general protocol that compares two arithmetic sharings. The last protocol in the rabbit collection is the loop protocol. We looked at this protocol because we care about practical applications, and as Samir explained at the beginning, the ReLU function is a fundamental component of privacy-preserving computations related to machine learning. Now, this ReLU protocol is a specialized version of the less than constant protocol, and it applies when our modulus is of the form 2 to the k, and the constants we need to compare against is half the size of our modulus. In these cases, we can perform the LTC comparison in a more efficient manner. That's an optimized version of the LTC protocol. And with that, I would like to pass the rabbit to Dragos.
Well, first of all, thank you, Eleftheria, for passing me the rabbit. It's I think it has reached a new land. It's the VR land. I'm trying to experiment new ways of delivering information, and let's see how this goes. This is in a rec room if everyone is interested. Looks cool, looks cool. So if the rabbit is here, might as well jump to the next slide, right? And to understand the contributions here, I think it's useful to understand what is a negative number, and a positive one as well. And what better way to do that than a nice meme? But in order to get concrete, we should see these things into more detail. So how exactly we convert from a positive number to a negative number? Here we have, oh, this is so cool. I like these sounds being visual. It's nice. Okay. Anyway, so we have 5 in its binary representation, and we use 4 bits to represent the number 5. To convert from 5 to -5, when we have 4 bits, we basically just compute the complement of 2. So in this example, it's going to be 2 to the 4 because we have 4-bit space, and then we subtract x, in our case 5, and we end up with 11. So now 11 in its binary form, it represents the number -5. So you can see that the last bit indicates the sign of that number. Okay, so far so good. In a more general case, what we have is basically, in the ring case, numbers ranging from 0 to 2 to k -1 are positive numbers, numbers ranging from 2 to the k minus 1 to 2 to the k, those are negative numbers. If we compute numbers over mod p, so this is a finite prime field, the positive numbers are from 0 to p over 2, so the first half, and then the second half are negative numbers. So general case, the first half of the input space are positive numbers, and then the second half are negative numbers. Okay, so far so good. Now, this is basically what we needed in order to understand the previous type of protocols of computing whether, let's say, x is smaller than y. So this is also called LTS in our paper, less than secret. So if we want to compare whether x is smaller than y, what we do usually, what the common approaches did usually is, if x is a k-bit number, we add minus y to it, and we end up with this number z, which has k plus 1 bits long, and we need to force this to make it positive. So we have this extra bit of information. Basically, this is just adding to the k, and then we mask z with enough entropy. So we usually mask this with k plus 2 plus sec bits, and we open that. And in the end, we want to have this operations done over the integers, because if it's going to overflow, if the numbers are going to overflow, if at any point there's going to be an overflow, all these approaches are going to fail, and comparisons are going to collapse. The end of the world. Well, not so fast. So we have these restrictions. These protocols have these restrictions that p always has to be greater than some bound. So in this case, it's 2 to the k plus 2 plus sec, in order to avoid overflow. Okay, same goes for the case where we need to compare x with a constant. Say this constant is 0, for example. If we want to compare whether x is smaller than 0 and x is a k-bit number, we need to force x to be positive. So we add 2 to the k to it. In this way, 2 to the k minus 1, apologize. So we add 2 to the k minus 1, and we have now it's for sure a positive number. And then we're going to mask this number with enough entropy, so with some extra, so it's going to be with k plus 1 plus sec random bits, and we need to have these operations avoid any overflow. So we're going to have that p is greater than this bound. So basically p needs to be greater than the input space, so that all the operations are going to be done over the integers, basically, with no wraparound. So in our approach, we don't need all those extra sec plus 1 bits for the entropy. What's really cool about our approach is that we can avoid those sec bits and make use of the full field length. So also a good benefit of this approach is that in here we needed to make sure that x is going to be k bits long, but here, and if inputs were going to be malicious, there's it's slightly hard to ensure that the inputs are k bits long, whereas in our case we don't need any restriction. We don't have any restrictions on x. Basically x can be any number going from 0 to p minus 1. So malicious parties can input whatever. Our protocols will still work because there's no input bound for x. So that's pretty cool. And when we're doing operations, we also need like less data to store things. So we're gonna see later that. Actually, I'm going to show you now. So what are the performance of these protocols of the rabbit family, as Eleftheria defined, or rabbit collection? And so we have a bunch of settings because we wanted to test our protocols in many settings. For the dishonest majorities, you have 2 parties. For the honest majority, we have 3 parties, and we also support the case when at most one of them acts maliciously. And well, these protocols were benchmarked in the local area network. In the paper also provide numbers for the wide area network. So when the round trip time is much larger and the bandwidth it's much smaller, you can check those numbers in the paper. But for now, for the purpose of this talk, we're going to focus on only the LAN network. So let's see Rabbit in action. Will it run? Well, for certainly it will run, but will it be fast enough? For the ring case, we see that the throughput is very close to the EDABIT protocol, where EDABIT protocol is at this point one of the fastest ways of computing comparisons. But Rabbit surpasses it in some cases. So for the ring case, it's the same. For this honest majority ring case, OT is the same. So throughput is roughly the same. Communication is roughly the same. For honest majority, same. So Rabbit, EDABIT are racing each other and there's a tie. But for the field case, we can see that for the OT case, the throughput is around 1,500, whereas for EDABIT, we get a throughput of 1,000 comparisons per second. So communication is also improved. So communication for this honest majority using OT, it's around 2,800 kilobits per comparison, whereas for EDABIT, it's around double. You can see that this, for the honest majority case, throughput is also better in the field case. So we can see that throughput is around 88,000, whereas here is around 41,000 for EDABITs. So we can see that, of course, Rabbit is better in these cases. For the field case mostly, the ring case is tied. So that's cool. And yeah, the last part is when we compare with honest majority passive, we can see that the throughput improvements in throughput is around 3 times and communication about twice. So twice lower communication. So that's good for Rabbit. Good Rabbit. And these are all tested using the same setting. So we have 16 threads running and we have 2 million comparisons to get like enough stable throughput. But there's also like a really interesting thing we discovered during our experiments. So for the HE case, we've noticed that Rabbit is kind of friendly in that scenario because for Rabbit, in order to store a number, we need less space because we don't have those extra segbits. So having a smaller plaintext space is gonna give you smaller ciphertexts, and that's gonna give you smaller zero knowledge proofs, smaller memory footprint of zero knowledge proofs, and that's really nice. So if you have your devices which are memory constrained, then we recommend you using Rabbit for the field case because the memory footprint is gonna be lower. Because we store less stuff. The underlying arithmetic is done over smaller numbers, basically. So conclusions: Rabbit is fast, and we show that if we remove the slack, we're going to have smaller protocols. There's also a small caveat to that. We made our protocols work with smooth primes, and it would be very interesting to see whether you can remove the slack even if the prime is not smooth. So we needed the smooth prime in order to compare apples to apples. In the case of MPSPs, it had some extra, so it has some statistical security, around 40. And this is not inherent to how Rabbit works, but it's more inherent to how this extended DABIT the extended DABIT construction works. Would be interesting to see whether you can get rid of this extra smooth, this prime smoothness, and still have efficient protocols. So we leave that as an open question. If anyone is keen to tackle that, then go for it. And you can also contact us if you want. So that's all. I hope you enjoyed, and I grabbed this by mistake. But thanks a lot for listening, and take care. Bye-bye.